Okay, afternoon guys, wherever all the time it is in your country. Been a little while. I did a live stream last night actually. First live stream in a while. Been very busy. Had a couple of people staying at mine as well. So yeah, been pretty tied up for the last couple of weeks. But now we're going to get back into the swing of things. I'm going to be doing some more regular live repairs and also some live subwoofer recones and hybrid builds as well. I've got a few of those to do, so I figured I'd probably go ahead and live stream those as well. So today we're going to be looking at this DC Audio 10K. Now this is I believe one of the slightly newer 10Ks. They vary in size. This is slightly more compact one. I have worked on a DC Audio 9K before, and I think the 9K was about this size or perhaps a little tiny bit bigger. So they've actually squeezed stuff down a little bit inside here to get it into a slightly smaller case, which is useful. We've got 3 sets of power inputs on here, so very high current abilities from this amplifier. And I'm going to take you through my diagnostic and repair procedure from the very start. I haven't even taken the back off this amplifier yet, so I have no idea what's going on inside. Yeah, I don't know what the issue is here. So we're going to start at the very beginning with the amplifier. Come into the workshop. I'm going to turn her over and just take the back off, see what we got inside. It's quite heavy. Despite being small, I'm just going to wipe off any bits of solder that might be floating around on my desk so we don't scratch the top here. We don't scratch it anyway, I mean it's wood, so wood doesn't scratch metal. Right. Just make sure. I do have this foam. Top thing that I put amplifiers on when I'm working on them, but this is a little bit small, I think, for this amplifier. Well, it could work. It's going to be a little bit of a seesaw, I think, if we put it on that. We could try it. This is obviously a little bit better for the case here. Doesn't scratch it as much. So let's pop this on here like that. Yeah, okay, that kind of works. We can roll with that. So let's take the back off and see what the issue is with this one then. Got a fair few screws on here. Now I do have a power screwdriver here. The battery is crap and therefore I've removed it, and I have been hooking my power cordless drill up to my bench power supply and setting the voltage correctly for 14.4 volts, and it works wicked. But the wire is not long enough to get over this side, so I need to hardwire something in to make that work better. So for the time being we're just going to unscrew these by hand just now. Bass Addiction says, I got my system playing. Check out my latest video if you're going back. I'm glad you're back. 2 15-inch FI Omegas on a 7.5K limitless. Sounds pretty good, my friend. Those FI woofers are fantastic. Must be very, very nice. Afternoon to Car Gift. How's it going, buddy? So we're going to see this repair from the very, very start. I've not opened this one at all yet. No idea what's going on inside. It doesn't smell. So that's before you even take the back off an amplifier, you can kind of get a rough idea as to whether it's just the output section failure or perhaps a bad power supply section failure. Generally, if an amplifier kicks out a whole bunch of smoke and it stanks when you get it in the workshop, that's most likely a power supply failure because the power supply cooks off the battery when it fails. If it doesn't smell and you don't have any burnt marks inside, but it's in protection, then it's probably just output section failure. So let's get this case off here. Alright, let's have a look. So it looks very nice. So, first port of call, we are going to just check to see if the power supply has any burnt areas or marks or anything on here. So the power supply doesn't look like there are any of the MOSFETs over here that are burnt. Take the correct camera angle here. Actually, I'm going to use my head cam because that might be a little easier for you guys to see what I'm seeing. So just going to take my hat here with a webcam strapped to it. Good bit of redneck camera angles going on here. Right, so this is going to be a little bit shaky. I'm going to try and not make it shaky, try and make it as least shaky as I can. So if we go over here, hopefully you can possibly see in here there are no scorched or burnt areas of the power supply. It looks pretty nice. These transformers are all seated down incredibly well, very, very strong. You know, these are going to be really, really resistant against vibration damage from the amplifier. I need to turn my hat a little bit up. It's a bit shaky here, so apologies for that. I'm going to try and get like a gyro or something for the cap. If we look at the output section here, again, doesn't appear to be any scorching or obvious blown FETs at this point in time, but it could be something hiding behind these MOSFET clamps. So, Josh Hansen says, "Hey Sam, I guess I'll be listening to you as I'm at work, but I won't miss the action for anything." Oh, wicked! Thanks, Josh. Thanks for staying tuned in, even if you're at work. That's fair enough. It's a random time for me to do a live stream. Obviously, I work from home, so this is my working hours, if you like. Okay, so we've taken the back off, and visual inspection, there doesn't appear to be any obvious burnt areas or anything like that. So I am going to go ahead and take a guess that we have just lost a couple of output MOSFETs on this one. I don't think there's anything too drastic going on here. Now, because this is such a big amplifier, it's very, very time consuming to actually take the whole thing out of the board. So if it's just a couple of FETs in the output section, I've been getting quite good at doing a top board repair. So that's where we make a repair to the amplifier without taking the thing out of the case. So we can remove the dead MOSFETs, clear off the holes with the tweezers and the desoldering pump and the iron, and then fit new MOSFETs in place. And I've even been able to replace the drive ICs on the drive board here without taking the driver board out of the amplifier, just by using the heat gun at an angle and using tweezers, being very careful to get the new ICs on there nicely. I have been pretty successful in doing that recently. So if the drivers are dead yeah, we might even still be able to do a top board repair like that. So let's take our multimeter and let's just confirm that we don't have a short circuit across the amplifier's power terminals. So to do that, let's put our multimeter onto the beep setting, and we're just going to go ahead and put it between positive and negative input on the amplifier over here, nice and easy. And if we have continuity, then there is an issue. If we don't have continuity, then it appears to be there is no short on the power supply section. So as you can see there, we have a number 1 on the multimeter, which dictates that the capacitors are fully charged, therefore there's very high resistance across these terminals. So therefore the power supply is most likely fine. That's a very quick way to check whether all the power supply FETs are shorted or not. Because they're all in parallel with the main power terminals here, if any of the power supply FETs are shorted, then it would present a direct short across the power terminals of the amplifier. So the fact that that isn't present means that we're probably okay on the power supply side. So let's turn our attention to the output section. Let's bring my camera over here. Now, the output section doesn't usually show visual signs of damage, so what we need to do is we need to take our multimeter and we need to get on in there and probe the MOSFET legs that are just under the clamps here. And we're looking for ones that are short, or banks of FETs here that are short. So I'm going to try and do this with my head cam, and hopefully it won't be too wobbling around. So we're going to go ahead and probe the first bank over here, which is probably going to be a high side, I believe. So on the multimeter screen there, we've got 564 on diode setting, which is about right. And we don't have a short circuit between any of those pins. That is charging some capacitors, so that appears to be fine. Alright, so that's a bank of 4. Let's move on to the next ones, which is this bank just here. So let's do the same for this. Yep, that looks about right. And let's just do the other pins here. Yep, that looks about right as well. So that bank is appears to be fine. Let's go ahead and do the one of the last banks over this side of the board. generally you can tell if there's going to be a short circuit on any of these FETs over this side of the board, there'd be a short between the drain and source on some of these FETs. This is just charging capacitors. So this side of the amplifier seems to be okay. Let's go ahead and do the same for the other side. Now I'm going to have to look down on myself, so the camera angle might not be too great here. So I'm just going to go ahead and change the camera angle back to here. Let's have a look. Okay, now this is interesting. So usually when you probe the gate and the source, you usually get a number that stays pretty constant on the multimeter. It doesn't climb like it's charging a capacitor. However, in this case, the gate and source appears to be just charging a capacitor. So I think we've got a short circuit somewhere, but it's not on this bank. So see here on the multimeter, we're now charging back down. So we're charging capacitors one way, and this is between the gate and the source. And we reach 283. So that is very unusual. So I think that there's a problem somewhere on this side of the amplifier, but just not in this bank. So let's go on to the next bank. Let's have a look, see if there's any short here. Nope, no short on this bank. Go along to the next bank. Okay, now this bank has a direct short between the drain and source of this bank of FETs. However, the short isn't between the gate and source. Usually when these output MOSFETs die, they short between all three of their legs. So we can tell which MOSFET is the bad one pretty much because it will have a short on the gate to source rather than just the drain to source. So let's keep going along and find the one that's bad. Okay, this one's got 79 ohms on the gate to the source, but it's not a direct short, so I think it's the one next to it because obviously we're just reading the resistance through the gate resistors at the moment. So let's go along to the next one. Okay, 77 ohms on this one again, so let's keep going along. Aha, there we go. So this one does have a direct short between gate and source. So this one is probably our culprit. Let's go along to the one next to it in parallel. Let's see whether that one's bad as well. Okay, this one has 78 ohms on it again. So it appears that there's only one dead FET in this whole bank. Interesting. That went down very undramatically. So because we only appear to have one single dead FET, we only need to replace the ones in the same parallel bank as that, which means that we can probably get away with doing a top board repair. We don't have to take the amplifier out of the case. I think we can probably get away with doing this with the amplifier board all still in the case like this, as long as we're careful and we know what we're doing. So let's get the MOSFET clamp off here. What I might do is, let's have a look. So it's, yeah, you can kind of see what's going on here. It's this one here. So if I remove these clamps just to get a better look at these FETs. That's one. That's two. That's three. Right, okay, so these appear to be the MOSFETs in question that have an issue on their banks. So let's just confirm which FET it was again that was the problem. I think it was maybe this one. Yeah, so this is the FET that's bad. This has the direct short across it. So what we can do is I can actually go ahead and wibble wobble this FET off the board because that one is shorted for sure. So if I take my pliers here, I'm just going to try and aim my camera more down at what I'm looking at so you can see it a bit better. So which one was it again now? It was this one here, right? So yeah, let's take this one off of the heatsink. Like so. And then what we're going to do is we're just going to wobble it backwards and forwards to break the legs of the MOSFETs. I'm going to try and snap it with higher up on the legs so that I've got something to grip with my tweezers to take them out of the board, but that might not be possible. Let's give this a wobble. Okay, one leg's gone. Two legs gone. Okay, 3 legs gone. Yeah, that worked quite well. I've still got some leg to grab hold of with my tweezers. So this MOSFET here, if we pop that there and we read that with our multimeter, yes, lo and behold, there is a direct short across all 3 legs of this FET. So this one is dead. Right, so now that's that one removed, I wonder whether any of the others around it shorted out as well. Let's take a look. So we're going to take our multimeter and do the same thing. Check between the gate and the source. So now on the multimeter screen here, we have much more positive looking values. It jumps straight to 489 on this one. If we swap the probes around, flip the probes around, we should see something in the thousands. Yep, 1277, 1286. That's looking pretty good. So I'm just going to go ahead and check along all the rest of these banks, make sure that we have pretty consistent looking numbers here. 361. Okay, there's another short over here, and this is between the gate and the... Oh, that's interesting. This short is between the gate and the drain. Okay, so there is another shorted FET somewhere along here. Let's try and find that one. It's looking quite promising. This is hopefully going to be a relatively quick repair. Usually with these amps that only kill 1 or 2 FETs, the driver often stays intact, fingers crossed, so I'll hopefully won't have to do an IRS 21844S replacement. Okay, so... Okay, there's a 77 ohm resistance between the gate and the drain of this FET. Let's check the one next to it. 77 ohms. Direct short on this one. So I believe this third FET in is also bad from this bank. So let's go ahead and remove that one. 1, 2, 3. That's this one here. So I believe that one's bad as well. Hello to all you guys on the live chat. Hi Matthew, good day from Tasmania. Wow, far out, buddy. Yep, so I think it was just that single FET there that we lost as well. I'm going to go ahead and check the rest of these batches along here. Looks like we've got one over this side as well. Okay, so there's another one more. So we're up to 3 dead FETs so far. There might be more than 3 dead FETs. Sometimes FETs don't just short, they can also do weird stuff inside the semiconductor layers. And they no longer become a FET, they just become a bunch of diodes or something. So just because it's not shorted doesn't mean that it's not damaged. But we can remove the ones that are obviously shorted. We can apply some small power to the amplifier and see what goes on the rails. And we can determine from that the health status of the rest of these FETs. So I'm going to snap off the rest of these FETs that I could clearly see were shorted. So we've got one over this side of the board. So let's remove that. There we go, and our third one that we can see here that's possibly shorted, let's go ahead and remove that one as well. Is DC audio good? Yeah, it's fantastic. DC audio make some of the best amplifiers you can get. For sure. Okay, right, that's our 3 obviously shorted FETs removed. So I don't think we have any more short circuits along the output section here. No more short circuits in the output section. Right, okay. So now that we have removed the obviously shorted FETs, there may still be some other FETs that are damaged but not shorted. And to see whether that is the case, we need to apply a little bit of power to the amplifier. So the amplifier works with 2 rails. Obviously you've got a high rail and a low rail, and you have 2 different sides of the output. You have low side and high side. So the low side should only have negative rail voltage on pin 1 and 3 and nothing on pin 2. The high side of output should only have voltage on pin number 2, should only have high rail on pin 2 and nothing on pin 1 and 3. So we can apply some power, and if there's voltage where there shouldn't be on any of these MOSFET legs, then we know that there's still a problem somewhere. So let's get our power supply hooked up here. This head cam is a little bit annoying because the wire trails over my face. I could get a longer USB extension cable and have it wrapped around the back of my head or something, so maybe I'll do that for a future video. So just positive and the ground going in here. There's not much current handling, so we don't need it to screw in very tightly, just need to get it shoved in so it makes a connection there. Okay. I'm going to allow sort of 6 or 7 amps to pass. So if you can see here on my screen here, I'm going to allow 6.7 amps to pass, and we are going to kick this thing not with 12.6 volts. I'm going to lower that down a tad actually. I'm going to probably kick it in with about 10 volts or so. .2, that should be about right. Now we're going to take our oscilloscope probe just here. We're going to give the amplifier some remote signal, and I'm going to probe different parts of this amplifier and read what's going on the high and low rails. So let's kick the remote just for a brief second, just to charge the output rails very, very slightly. So if I probe the rectifier here, we should see it would help perhaps if my okay, so this isn't grounded properly. My ground wire is not connected quite properly yet. Okay, now let's try that again. Okay, there we go. So you can see there, we've now got 12 volts on the rail. So we've got 12 volts on the positive rail, and we have, so that's positive rail again. Where's the negative rail? And we have 11.7 volts on the negative rail. So that's our positive and negative rails. So if we go along on the output section, we have the we should have the high side here, starting here. So on pin number 1, the gate, we should have 0 volts, which is correct, we do. Second pin, we should have positive rail, which is correct, we do. And the third one, we should have 0 volts, which is correct, we do. So just so you can see what I'm doing here. First pin, nothing. Second pin, high voltage rail. Third pin, nothing. So that's the high side, and that is correct. That's working as it should. Now let's go along to one of the low side banks over here. So low side bank, we should have negative rail on the first pin, which is correct, we do. On the second pin, we should have nothing, which is correct. And the third pin, we should have negative rail, which is correct. So that seems to be fine. Doesn't seem to be any leaking MOSFETs over this side of the board. Let's just check the rest of these. That high side looks good. This is a high side that also looks good. This is a low side that looks good. Okay, now let's check the other side of the board. Low side, yep, that looks good. Let's go over here to this high side. That looks good. That looks good as well. Okay, so that's an indication that possibly the driver chips are okay. Usually if the driver chips are heavily damaged or shorted out, what they'll do is they'll send the incorrect voltage to the high side, which then puts voltage on pin 2 of the low side FET, which is incorrect. Good morning, Beverage. Greetings from Brazil. Thank you very much. Greetings, buddy. Good for having you on the stream. Yeah, so Now what I'm going to do is I'm going to leave the remote powered on for a little bit longer, and we're going to build the rail voltages a tad higher, just make sure that the thing is good. So I'm going to turn, you can see there that the rail is charging on the scope screen there. We're up at 23 volts now, so this is going to be up to some pretty high voltage, so we're now at 41 volts on the rails. Now I'm just going to double check that the FETs are still good. So we've got low voltage rail, we've still got nothing on the pin 2, which is correct, and the high voltage rail, that's also correct. Yep. Okay, cool. So I'm going to continue charging this, and rather than probing the rectifier to read the rail voltage, I'm going to probe the low side gate, which should allow me to see a drive wave when the thing starts kicking into life. So let's go ahead and charge this a bit more. I'm going to give you my scope screen nice and big so you can see exactly what I'm doing here. So we're probing the low side gate, which has the low rail on it. We've got 33 volts on there now, so we're slowly charging that, and at some point a square wave will appear on the screen there. And hopefully the amplifier doesn't explode, because the FETs are bad. There you go, did you see that? There was a baby little square wave on the screen that just happened there, and that will have meant the amplifier was running into operation. So let me zoom in on that square wave. That's the low side drive wave, and that's very important. This has to look very good in shape and form. So let's zoom in on that drive wave and let's see what it looks like. There we go, very nice. Okay, so the amplifier appears to be functioning fine. If it wasn't, then that wouldn't happen. That would look very, very bad. Let's go over to the other side of the board and just check the low side drive on the other side of the board looks okay as well. Yes, it does. So it appears that all of the IRS 2184S drivers are still intact, which is a big relief for me, which means I haven't got to do a driver board replacement, a driver IC replacement from the top board repair, which I don't like to do. It's just a bit of a headache. Let's check the high side drive. There we go, that's our high side drive. So the amplifier is only pulling, wow, for a big 10K amplifier, this is pulling not much current at all. You can see here on my screen, it's only pulling 5.5 amps there at 10.2 volts worth of operation. So that's pretty nice. Yes, it seems that we only had 3 dead FETs and all the others appeared to have survived. So what are these FETs, you might ask? These are probably going to be either 24N50 or 24N40s. So these are TO3PN parts. So here we have 24N40F. This is the MOSFET part that this amplifier uses in the output section. Now fortunately, the camera's not going to focus. There we go. 24N40F, so it's the bottom code that we're looking for here. Now unfortunately I have a whole drawer full of these, so I can go ahead and drop some replacements in. Now the drawer that I've got full of these parts, some of them are actually salvaged from other amplifiers that may or may not have been made at roughly the same time as this one. So if I take the MOSFETs that I just removed from this board, and we can have a look at the batch code. The batch code of these MOSFETs is 1D17AS. 1D17AS, as you can see there. We've also got one over here that's a 1G32AE. Now, usually you have to match up the batches perfectly in parallel with these amplifiers. But provided that I've got some 24N40Fs, which are they're very good FETs for running in parallel. They're quite happy running in parallel with each other, even if the specs slightly differ. So if I can find some FETs that have a batch that is similar, a 1D17 or a 1G32 or somewhere around those numbers, I will probably be quite safe in banging those in the board in parallel with the different batches. So let's take a look and see what we have in my drawer here. So what was I looking for? 1D17. Ah, Nicholas, H1 Nicholas is on the stream. Oh, very, very good. Haven't seen you in a while, my friend. I hope you've been well. 1D17AS. 1D17AS. 1G32AE. Now, the way that we can tell whether these FETs are happy running in parallel, there are a few ways. First of all, we can use our thermal imaging camera just here. So once we put the FETs in place on the board, we can see whether those batches heat up. If they're heating up on idle, then it means that the FETs are fighting each other, which means the specs are too far off each other to be run in parallel. That's one way of checking. Another way of checking is obviously we can look at the current drawn from the amplifier over here. On idle with all the bad FETs out, we were drawing 5.5 amps there. there. If we put the new FETs in and suddenly it starts drawing over 6 amps, then we know that there is a problem because more current is being drawn on idle than it was a moment ago. Well, now would you look at that? I just pulled a FET out of my drawer here, and I have 1D17AB. So that is an incredibly similar batch. We've got 1D17AS, 1D17AB. Nice. So it looks like I might indeed have some FETs here which are a close enough batch that I can just go ahead and drop these in without changing the whole bank of these. So I've got two 1D17ABs, and the other one here was a 1G32AE. Okay, let's see if I have any 1Gs in here. 1G47AC, that's a little bit far off. I do, but 1D33, 1D, let's have a look. 1G37AC I've got. That's close, that's close. 1G37, 1G32, that might work fine. But the interesting thing is actually going to be looking at what the FETs are in parallel with it on the board, because I want to match them up with the ones that are already there. So I've got some FETs that will work. So let's go one, so that we've got 1D33AL in here, 1D30, so this one needs a 1D33 really in order to work properly. And this one over here, this is a 1D33. So these are all 1D33s. That's very interesting. It seems that the FETs that I pulled off are actually ones that are different batches, which is interesting. All the other FETs in this board are all 1D33AL, but the three FETs I pulled off were different batches, which probably means that they were not paralleling properly and therefore they've died first, which is probably one of the reasons this amplifier went down in the first place. So really I should be looking for a 1D33AL batch if I can. I don't think I have anything that matches that similarly. I've got 1D17, 1G37, I've got 1D, here we go, I've got 1D33AH. That's close enough. 1D33AH. I've got a couple of these. I know I've got a few of these 1D33AH batch FETs. Now these will work fine. These are close enough in batch with the ones that are already in the board that this should just work fine. 1D33AH. Yeah, I know I've got a whole bunch of these in here somewhere. There we go, there's another one. So I need one more to complete my trio of FETs to replace. One D33AH. There we go, perfect. So I found myself three FETs which are a 1D33 batch, which is the same as what is in the board here, 1D33. In the board we've got AL, in my hand we've got AH, which is very, very close enough. I think that we're not going to have any problems running these in the board like so. Now these FETs have obviously pulled from a amplifier that I worked on before. They were probably FETs from a side of the amplifier that didn't get damaged when it went down. But just to be on the safe side, I'm going to go ahead and check these in the transistor test to make sure that they are all hunky-dory. I've made a modification here to my transistor tester so I can quickly test these 247AC parts. So rather than having to shove that in there and bend the legs to get it to fit, I can just put the middle leg in the center here, and then it touches against the two bits of copper wire that come from the other two probes, which makes life a lot easier for me in quickly testing these parts. So we've got 4.5 on the VT, gate capacitance of 3.6 and an RDS of 0.8. I'm not too interested in the RDS at this point because I know this tester doesn't read the RDS quite properly, but as long as it's all consistent enough then we should be fine. .4, I can't remember. What was the VT on the other one? My brain is not working today. There we go, 4.5. Yeah, that's fine. Mate, I've got MOSFETs coming out of my ears. I've got so many. I've got the most 69N25s I've ever had in my life. Yeah, so these FETs all check out very, very nicely. They all check out fine. So what we can do now is we can literally, I think we should be able to just drop these FETs in, and it should be a successful repair. So what I need to do now is I need to take my soldering iron. I'm going to take my soldering iron here, and we're going to have to remove the legs that are left in the board from the old FETs, pull them out with the tweezers, suck the remaining solder from the holes, and then slide the new FETs in and apply some solder. So let's see if I can. I'm going to take my hat off just here. I'm going to try and get this so you can see it nice and clearly with the camera rather than just using my head. So let's have a look. So as you can see here on the board, let's let it focus for a second. Come on, there we go. So yeah, this is the obviously the location that I removed the old FETs from. So what we've got to do is to do a top board repair like this. We've got to heat up the pad here, and then we've got to take our tweezers. Whilst the soldering iron is on the pad, we've got to pull the pins out from the hole, which will leave the solder in the hole, and then we've got to suck the solder from each of the holes. So we've got enough of the leg left there on these ones to pull that out quite nicely. On this one over here is a similar story. There looks like there's enough of the legs left in there to pull out quite nicely. And if we go over to our third one over here, yeah, that looks pretty good as well. So this shouldn't be too much of a challenge to remove these pins from their holes. This does require a bit of concentration here, so I might go quiet just for a moment, because what I don't want to do is I don't want to push the pin underneath the board. Now, I might actually need to spin the board around, because I'm more used to doing these with the board the other way around. So just bear with me, I'm going to flip the board around so I can do it in my comfort zone here. Okay, there we go. That's a bit better. That's more. I think I just knocked my scope down there. That's more in the orientation that I'm used to for doing this sort of stuff. Right, so let's go ahead and change the camera over to this side. So the FETs that I'm working on are actually way down in here now, and you won't be able to see this, unfortunately, because the cameras are not angled this way. So I'm just gonna have to take my word for it that we're doing this. There we go, that's one pin removed. It dropped off the tweezers before I could show you. Let's go for the second one. Okay, second pin removed. Hopefully I can show you that. It won't focus because it's the board is the more common thing on the screen, but yeah. So there's the pin is removed with the tweezers here, and it's got to do the third one. There we go, third pin is removed. So that's one FET pad sorted and got the pins removed. Let's move along to the next one just here. I'm glad that I'm making work go by much better, Josh. I'm sorry if you're unable to actually watch visually what's going on, but I guess you can't actually see anything at this angle anyway. But yeah, get this pin out here. Oh, 1. 2. Come on, baby. Give me a hat trick. 3. Okay. Whew. Successful so far. We've got 1 more FET location to go. I don't want to push these pins down inside. I just want to lift them up very, very gently. So let's do this one here. There we go. 1, 2 left. This second one is tiny. I might struggle with this one. I think I'm going to struggle with this one. I need to apply some fresh solder to this to get it to heat up properly so the pin comes loose, because it's very, very far down in there. The tweezers are struggling to grab it at this point in time. Okay, fresh solder, come on. There we go, it's sunk in, Right, now let's get our tweezers. Come on, baby. No, the pin's too far down, so this one's going to have to be a job for our solder sucker, and it hopefully should suck the pin out with the solder. Yes, success! We have a hole now in the board on that pad. Perfect, so that worked. Right, last one. There we go, success. All the pins are out. So now all I've got to do is I've just got to suck the solder from the holes. So to do that effectively, we're going to apply some fresh solder to each of these pads where the MOSFET legs need to go in, just so that the solder pulls out nice and fresh, leaving a nice big hole for the new MOSFET legs to go in. So apply some fresh solder to each of these pads. Remember, we were seeing 5.5 amps worth of current draw on idle before, so we should see close to that if these FETs are happy being run in this amplifier in parallel. Where do you order the FETs same badge? You just get lucky with what ones come. And the FETs that I'm using are actually taken from another working amplifier. So yeah, they were obviously made in the same factory around the same time. The factories that make these amplifiers will buy their FETs in the hundreds of thousands per order. So the chances are that if you look at 2 amplifiers produced in the same factory in roughly the same sort of within the same sort of 3-year period, then they'll have very similar batch FETs because they will have ordered them all in bulk. So yeah, if you salvage FETs from a working side of one amplifier, then chances are if you keep them to one side, you can use them in a different amplifier that was made in the same place, for example, or the same country, and the FETs will be of a similar enough batch you can just drop them in without having to replace a whole bank. Okay, almost done. Last area here. This is going to be the quickest 10k amplifier repair I've ever done if this works. Okay, right, that's all of the solder removed from the holes. And just so you can understand exactly what I was doing there, I'll take my close-up camera again and show you exactly what I was just doing. So as you can see when this focuses up here, there's now no longer any pins in the holes there for those MOSFETs, and the solder has been sucked clean from the holes. So I can now go ahead and drop those replacement MOSFETs in and solder them up, and it should work fine. There we go, see? That's what I was doing, and those pins that I removed are tiny. They're like this big. You can see there. Those are the things that I've been removing from the amplifier. Alright. It's spelled Google's, but says, I'm after some tips to get an extra dB or two. I sealed the boot vents, did the big three, and also screwed the subbox to the chassis. What else could I do? Without knowing what your system is and without seeing the car, it's very hard to kind of just give a general. I mean, those are pretty general things to do to gain you some dBs. Without seeing your install, I wouldn't really know what to advise you in terms of positioning or amplifier settings or whatnot. Right, so these are our replacement FETs that we're going to drop into here. I'm just going to get rid of the excess solder on these legs so that they go in smoothly, because they're a little bit thick from having a bit of solder on them. And to do that, I'm going to use some solder wick. I've got some of my solder wick here. Josh says, have I been doing enough repairs here lately? I know exactly what you're doing and what the board looks like just by hearing you explain it. Oh wow, that's pretty cool, man. That's wicked. I'm a very visual person. I would probably, I mean, yeah, if I was listening to a repair like this, I'd probably better get the grasp of what's going on, but I do like to see things. I'm a very visual person, you see. This solder wick works really, really well. Much better than the other crap stuff that I purchased myself. This stuff was recommended to me by Gordon Taylor, the amp doctor. Yeah, this stuff works beautifully. It's much thicker than the stuff that I tried to buy, and it has wick, flux in the wick itself, which helps out get that solder up the wick. Right. Okay, cool. Let's go ahead and drop these FETs in and see if the thing still works then. I should probably check first that I think the rails are sunk down, otherwise I wouldn't be able to desolder that. Okay, so let's slide the first FET in place here. Okay, lovely jubbly, that works well. The height is just about right as well on the legs of the FET. Let's do number 2, let's put that one over here. Do you ever wear that wig while repairing an amp? Hell no. Of course not. That would get all up in my face. I only wear that wig when I want to hair trick myself. Okay, that's the second FET in place, and the third one just here. Let's drop that in. Okay, that's the third FET in place. Now I just need to solder the legs in, and we should be good to test this out. This wire is right in my goddamn way. Let's you stay out of the way there, my friend. Okay, it's quite hard to see all this with the head cam on, so I'm just going to take that off. I'm just going to inspect my solder joints just there, get it nice and close up just to make sure that they are all good to go. We haven't got any bridges or anything like that. Okay, right, I think we are good to go. Turn the iron off, and just before we apply the power again, I need to flip the board around to get the power by next to my power supply, but I'm just going to check on the multimeter, make sure there are no shorts. And one last time. Make sure I haven't created any solder bridges or anything like that. Okay, no solder bridges anywhere that I can make out. So let's turn this baby back round and apply some power. And while I'm turning it around, I'm also going to try and lift it up above my head for any of the loose bits of solder to fall out that may have made their way into there. So I need to be nice and strong. This is a very, very heavy amplifier to be doing this with. Okay, let's flip it around. Julio says, I love your videos. Cheers. Thank you very much for the nice comment. Especially half ohm daily. Yeah, that's fine. What happened? Hey Sam, long time. What happened though with this one, Traces? Now this one just was 3 dead FETs that were the wrong. These FETs were the wrong batches. They were actually completely different to the other ones around it, and all 3 of those died. So I think that was why they were wrong batches. I just made a Class AB amplifier, 6 times 2N3055 outputs an hour ago, and testing it by watching your videos. Fantastic, Mr. Am. That's really, really cool. Make a video of that if you haven't already. I'd love to see a video of your Class AB amplifier. I'm not so clued up on Class ABs as the same as I am with Class Ds, so that would be really, really interesting to see. Okay, morning's Crazy Logics. How's it going? It's afternoon here, my friend. Okay. Right, let's plug this power back in, and hopefully this is going to work and not explode. I'm just trying to trim off some of this excess wire so I can get the ground in here better. Come on, off you come. There we go, that's a bit more excess wire to play with. Right, let's put that in there. And last and not least, the remote cable. Right, let's power this baby up and see what she's got. So we're going to go ahead and probe the low side, I think, so we can actually see the low side drive. Oh, my scope cam, my power supply cam has moved. Let's move that back. Got a wire going across it now for some reason. There you go, that's a bit better. So we're mainly interested in the current from this amplifier, so I'm just going to go ahead and show you the current as at 0, 0 at the moment. And this should be about 5.5, shouldn't it? That's where it was before. So let's go ahead and give this a little bit of power. We should start to build the rail there. As you can see, we've got 17 volts on the negative rail just now. I'm going to allow 7.3 amps to pass just to let it turn on a bit quicker. So we should have negative rail there, yes, correct. And on the high side, we should have nothing, positive, nothing. And on the low side, we should have low, nothing, low. Alright, that's looking good. So let's continue with our charging of the output section. And I'm just going to give you my scope cam full screen so you can see what this is doing. Okay, looks good. let's zoom in on that drive wave. I wasn't entirely sure. That looked a bit wobbly there. Let's see. Oh no, it looks good. Okay, so on the current handling, on the current draw, we got 5.5 amps again. Perfect. So that is exactly the same. That hasn't changed, so I don't think this thing is drawing any more current than it was before. So what we're going to do now, that's been on for a couple of seconds. I'm going to take my thermal imaging camera just here, and I'm going to turn the amplifier back on in just a sec, and we're going to see whether these FETs that we've just replaced are getting hot or not. They shouldn't get hot in the least. If they're being paralleled correctly, it should stay very, very cold. So already I can see here on my screen here for my thermal imaging camera that they are all absolutely dead stone cold, no heat on them whatsoever, which is absolutely beautiful. Let's go ahead and turn the thing on again, and let's just confirm that. So yeah, amplifier's on, into operation. Yeah, these are absolutely stone cold. Not an inch of warmth on these FETs, and if they were being paralleled poorly, if they weren't happy running with the ones next to it, then they would heat up pretty damn fast, and they are absolutely stone cold. So I'm very, very happy with that. That appears to have been a nice, quick, easy repair. 3 FETs down. The reason for failure on this amplifier is because these FETs that went down were the wrong batches to be in parallel with the ones next to them. I was able to remove those 3 FETs that were dead and shorted. The others all survived. I looked in my drawer. I happened to have some FETs that were a similar enough batch to work perfectly in parallel with the ones that this amplifier came with. Fitted those, didn't need to change any gate resistors, didn't need to change any drive ICs, didn't even have to take the amplifier out of the case. We were just able to do a quick top board repair on this, and that is a nice healthy saving for the customer. This repair isn't going to cost much at all. I just replaced 3 FETs, I didn't even take the thing out of the case. So nice cheap repair for the customer, and happy days all round, I think. This one obviously needs to go ahead and do some endurance testing on this to make sure that the repair is definitely solid. So I always do a bench test and endurance test once the amplifier has been fixed. Obviously I can't bench test this thing to full power because it's 10k, so I don't have that sort of supply here, but I can do an endurance test at about 4,000 or 5,000 watts RMS of output, and that over a 45-minute period will confirm that this amplifier is good to go. How wide is your customer range? We have nothing like you in Australia. Unless you do it yourself, it's normally chuck it and get another. That's a shame. There should be some, I'm sure there's some people in Australia that are more than capable of doing this. I don't rank myself particularly high on the IQ scheme of things. I'm just a logical thinker. I'm a problem solver. I'm quite determined and I'm a logical thinker, but you know, I'm not like some super IQ head person. So if somebody wants to do this enough and has a bit of time to do some reading, pretty much, yeah, anyone can pick this up really. So yeah, there'll definitely be someone over in Australia that will be able to do this, no problem. If anybody from Australia is watching me right now, then maybe there's a gap in the market here. It doesn't appear to be any amp repair techs in Australia, so maybe think about starting it up. Charles Phillips says, show me the rails. What do you mean? What do you want to see? Do you want to see what voltage the rails are, or do you want to see the drive? So, okay, let's give the amplifier its some higher voltage operation. So let's crank the voltage on here up to what it would see in a vehicle. Let's get that wire out of the way there. So in a vehicle, the amplifier would see 14.4 or 14.8 volts. So let's turn that up. We've got 14.6, 14.5, 14. This power supply likes to jump around a little bit, so let's just get it so it's happy. Okay, that's about right. So I'm going to crank the current up a little bit as well. I'm going to allow 8 amps to pass. It should be enough, I think. Let's give it 9, right? 9 amps. So 14 point. Stay where you are. So 14 point something anyway. 14 point something. We're going to see what the voltage of the rails are. So let's go ahead and zoom in on my scope. So if we probe the low side again, I'm going to take it off of AC coupling, put it back to DC coupling. Zoom out, 50 volts. Let's turn this thing on again. So you can see the voltage is climbing there, 10 volts as the current is drawn, 11 volts, 12 volts, etc, etc. 13. We're down at 155 volts. 14.4, there we go. So we're drawing about 8 amps at 14.4 volts. Yeah, if we zoom in a little bit on this, can we see? There we go. You can see the square wave riding along the low side drive there. So we've got 160 volts, 159.8 volts on the low side, on the low rail there. On the high rail, so the square wave is so large that my scope can't actually read the voltage on that. But the high rail will be, let's have a look. That's the low rail, that's 164. So yeah, the rails will be about plus minus 164. If we probe the high side rail, we've got 165.8 volts. So plus minus 165 volts with a 14.5 volts worth of input to the amplifier. Now this amplifier, I think, is 18 volt stable, and it will probably, well, I'm not sure, no, because it's only using 24N40F, so we can get a rough idea of the amplifier's rail voltages and stability by looking at the output MOSFETs. So these are 24N40s, so these are 400 volt parts, and so we need, therefore they can only handle up to a 400 volt potential difference between the rails. So this amplifier can only really run up to a maximum of 200 volts plus minus, and that's really on the edge of those FETs. So, you know, I don't like to push it that close. I would say probably 170. I mean, what are we at? 168. So yeah, this amplifier is probably only 15 volts stable. Anything above 15.5 volts is going to be getting scarily close to the voltage limit of the breakdown limit of the FETs, being a 200 volt plus minus difference there. So the closer the rail voltage gets to 200, the closer it gets to the FET's voltage breakdown limit. We want to try and stay away from that. So yeah, this amplifier isn't a high voltage amplifier. This is a low voltage, high current amplifier. So this won't be able to probably run at 16 volts very happily. And the FETs will perform better at a lower voltage. So I would try and keep this thing on a regular charge system, 14 volts charge, 12 volts battery. So I think we have a successful repair on our hands. Yeah, we just plugged 14.5 volts into this thing and it continued to work. So I'm very happy with the repair. We can tell the customer this thing is good to go. If you can tell, but I've got a fan up there now, so whenever I blow the vape, it blows it back in my face. Right. Okay, cool. Successful repair number 1. I'm going to stop the live stream here, as that's the end of this repair. I'm going to go take a break, have a drink, have something to eat, I think, and then I'm going to come back at you a little bit later, probably in about 1, 2, 3, 4, probably in about 3 or 4 hours, and we're going to be looking at a very cool amplifier, which was sent to me by a good friend overseas. This is a Steg 5K. I've never heard of the brand Steg before, never seen one in my life until just now. So we're going to get the Steg amplifier out on the bench and see if we can do a live repair, and the customer will probably be watching on the live stream as well, so that'll be a really interesting one. So I'm going to be doing a live repair while the customer himself is watching the repair, so can't go ahead and make any mistakes or any dodgy bodge fixes, because he'll be able to see exactly what I'm doing. H1 Nicholas is bang on. Yeah, absolutely. VCC divided by 1.5 for good reliability. I see that in a lot of amplifiers. In some of the ground zero amplifiers, I've seen them use way higher voltage FETs than they perhaps needed to, but it's because of this reason that Nicholas states. If there are any voltage spikes or anything strange that happens that puts a spike on one of the FETs, if the rail voltage is already very close to the FET's breakdown voltage, then that spike will shoot it over the limit and could kill the FET. Whereas if you keep your rail voltage well under within the limits of the FET, not only does the FET probably perform better at the lower voltage. If you look on the, if you've ever looked at a spec sheet for a MOSFET, if you scroll down to the lower end of the spec sheet, you'll see a whole bunch of graphs, and you might not know what the hell they mean, you might just scroll past them. If you actually study them a little bit, you can see that there's lots of different graphs that are all telling you different things, temperature versus current output, voltage versus current output, all sorts of different things, and there'll be a graph on there that tells you at what voltage the FET will perform best and will provide the most current, and that is the voltage on not just on the source but also on the gate as well. So on some FETs, the higher the drive voltage on the gate, the more current the thing can pass. Yeah. So those graphs are very interesting if you study them and you sort of start to look at actually what they're doing and how the FET is going to work. Because you might have two FETs, right? I've done this before. You might have two FETs that you can't choose between. One of them looks like it's way more powerful than the other. Let's go for power supply FETs. Let's say you got one FET which is a 60 volt FET, and it can do 110 amps as the ID, another FET, which is a 60 volt FET as well, can do 180 amps on the ID. But when you start to look, as obviously there's a 60 volt FET, but these FETs are ran at sort of between 12 and 16 volts. And when you look at the two FETs, one of them will perform better at 12 to 16 volts than the other one. And so it's very important to not just choose the FET that has the highest ID. That's not necessarily what you're looking for. You're looking for the FET that can pass the most current at the voltage you're using it at. So that's why it's important not just to look at the specs in the table, but to check the graph curvatures to see whereabouts in that FET's voltage range it performs optimally. Alright, so I'm actually coming to Oklahoma. I'm coming to Oklahoma, Dallas, and Chicago. I'm only stopping over in Chicago because the flight stops over there, so I don't think I can exit the airport in Chicago. But I'm coming over to Oklahoma, and also I'm going to a show. I'm going to Knowledge Fest in Dallas. So I think that's what it's called. If any of you are going to Knowledge Fest in Dallas, I will be there. It'd be lovely to meet some of you guys. So I'm actually coming to the States on the 12th of August, and I'm staying for a week with Chan and Jassa at DDHQ in Oklahoma till the 19th of August. So from the 12th to the 19th, I'll be in Oklahoma, and at some point, I can't remember the date of the show, I'll be in Dallas for Knowledge Fest. So yeah, if you're going that way anyway, could be pretty interesting. If you wanted to say hi, chat about some stuff, I'd be more than happy to entertain anybody that wants to meet me. How do you power the amp for endurance test? I power it with my Dell server power supplies. These are 175 amps each. I've got two of them giving me 350 amps of rated current output. And I use my dummy loads and a reactive load and some pulses and sine wave sweeps and stuff like that to put the amplifier under quite heavy load, playing different frequencies and tones. Okay, I'm going to stop the live stream here, and I'll probably see you in about 3 or 4 hours when we're going to look at the Steg 5K amplifier. So I'll see you later.